Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 6.3.4. Finding the Smith normal form of the incidence matrix is like changing a graph into a forest. What is a forest? A forest is a lot of trees. In fact, it's a graph that has lots of connected components, and each connected component is a tree. What is a tree? It's basically a graph that doesn't have any cycles. This is a cycle, so it's not a tree. However, if we were to remove one of the edges, like then the result would be a tree because there would be no cycles, no loops, nothing that you can't like go around um, in any way from one thing to another by just kind of following a direct path here. So let's take a look at what happens when we find the Smith normal form of the incidence matrix associated with this graph right here, this digraph. So we have our different edges denoted here. And let's think about this incidence matrix as a vector space map. And then, so you can think of this as like G of E1, G of E2, G of E3. So remember, the domain of this incidence map is a vector space where the where the standard basis vectors are the edges, and you're going to a vector space where the standard basis vectors are vertices. Okay, so 3 edges, so dimension 3, and 3 vertices, so dimension 3. So this matrix is a 3 by 3. And okay, so notice that actually this this column right here is the sum of those two columns. That means that this one tags along in the span of these vectors right here. It's inside of the span of these, so we can kind of reduce this to just the span of these if we're looking for dimension. Because we know this kind of tags along with these two columns over here. You can think of it, this way. Here's a little description of what I just said. Thinking about, so if you add this image plus this image, like this column plus this column, even with this notation, we end up getting GV1. Okay, so we can use that idea when we're computing Smith normal form. Like we could replace this column with itself plus that guy. And if we did that, we end up getting this. And notice that these two columns now are the same. So you can subtract, this column from that one and making zeros there. So see how we made zeros there? That was like getting rid of an edge. We just got rid of an edge. We just got rid of E1. So when we zero out a column, it's like we're getting rid of an edge. Now we do that until we can't do it anymore. Now we can only get rid of an edge if there's a cycle, because that means that one thing is in the span of the others. Because if you take like this plus this plus this, or some combination of them, you end up getting 0. And when does that happen? Like you have some kind of dependency relation between things. So one thing's in the span of something else only when you have cycles. So if you get rid of that by making a 0 column, you've actually got rid of an edge and you made a tree. So when we're finding Smith normal form, we're actually kind of working toward having a tree. All right. So we end up having something like, okay, so we end up having something like this. Now notice this is interesting. Okay, so we started here, and now we are here, and see kind of what we've, let's see what we've done. Actually, this is interesting. It looks like in the process, it's like we've zeroed this one guy out, but we've actually moved the first guy to this position, haven't we? This is like the first edge, and this is like the last edge, but the middle edge has actually disappeared. So we've actually gotten rid of the middle edge. Well, nonetheless, we've gotten rid of one of the edges. And by zeroing things out, even kind of if we've moved things around. All right. But nonetheless, look at the Smith normal form, and the dimension of the range of the Smith normal form is actually the let's see, is one less than the number of vertices we see, but it's also the number of edges. It's also the number of edges that we see, isn't it? After we've gotten rid of one, so we just have the number of edges of a tree, which is one less than the number of vertices. Okay. All right. All right. Let's see here. Then here, mention of the range is 2, which is one less than the number of vertices, but we could have done this right in the graph itself. Right. So essentially, instead of doing Smith normal form, you could just looked at your graph and done the same basic type of thing. So here's another example. Let's have the idea. Here, notice how we made one of the edges negative. That was so that the oriented direction of the edges is a loop. So when you add things together in that loop, you get 0. So you can perform some kind of operation here. Now, so you actually do have a relation every time you have a loop. Now, in the Smith normal form, we get rid of one of these edges, so one of them in the process, so we don't have a loop anymore. And the result is that we only have 2 edges. Notice the number of edges is always for a tree will always be one less than the number of vertices that you see, because it's like you had a loop around, but then you get rid of one thing, and then and in a loop, actually, we have a one-to-one correspondence between the edges and the vertices, and it's just a simple loop. But if you take one thing away, there's one less edges than there are vertices. Okay. All right. Spanning tree of the graph. What is a spanning tree? A spanning tree is it's a subgraph, so of a graph where every single vertex is hit, but it's a tree. Okay, so we have a tree spanning the whole entire graph. That means hitting every single vertex, but and it's a subgraph, and it's a tree. Okay, it's every vertex. That's called a spanning graph, a spanning tree. All right. So we will conclude. Well, let's go on to the next example here. Okay, let's take a look at this graph. We can form a spanning tree from this graph by removing edges. We can remove a lot of edges. In fact, this is a spanning tree right here. So here's a graph, and here's a spanning tree of that graph. In the next subsection, we'll talk about how to count the number of spanning trees. Thanks for watching.